Good afternoon. Okay, let's go ahead and get started. So, we've been talking a lot about probability lately, and we've been doing all sorts of things with it. But mostly the idea of probability is that we can use data and numbers to sort of predict what might be the outcome of a certain question. Now, are we going to get that right every single time if we actually observe? No. Our observation might be off from our prediction. But a prediction using probability is what will likely happen. Not what will happen, but what will likely happen. Now we can use this to apply to overall sets of data. In particular, today I want to look at normally distributed data. So I've mentioned this in the past, but normally distributed data, if we were to plot it with its frequency, the frequencies would be, sloping up and then back down. what would be a perfectly symmetrical curve. Okay, so here in the middle, where this peak is, represents the data point that has the highest frequency, or in other words, the data point that occurs the most often. Now, what do we call that data point? What do we call the data point that happens the most? That occurs the most? The mode, yeah. Okay. Now, we've also said in past chapters that if it's normally distributed, nice and even curve like this, it's not skewed to one side or the other, there's no two modes or anything like that, that this also represents the median and the mean. Okay? So using this information, what we can say is that since this also represents the median, the middle of our data, that we can split our data into two halves. 50% of our data occurs above the average, and 50% of our data occurs below the average. Make sense? Now, if we want to split it up more past that, it gets a little bit tricky. We can't just split it in half again and then half again. We need to understand how this curve actually works as to where those halves are. You know, I can't just physically measure it. I have to calculate it and see where those halves land. Okay? And to do that, we have standard deviations. Remember that standard deviation is equal to the square root of variance, which is the sum of all x values minus the mean squared divided by n, the number of data points we have. So these standard deviations are a measurement of location. They show us how to split up our data farther. For instance, one standard deviation from the mean is where we can expect most of our data to be. So one standard deviation in this direction and one standard deviation in this direction. This area between these two standard deviations is where most of our data occurs. Right? Okay. Now we can actually take it a step further now and apply probability to this to find very specific locations of data. Before we were just getting kind of general ideas like, okay, how many standard deviations away is a particular data point. Now we can actually find very specific points. So let's say that where is it? Yeah, there we go. Let's say that we visit a light bulb factory, okay? And we get some numbers from the light bulbs that they produce there. The mean, or the average, light bulb that they produce will have a lifespan of 1,000 hours. Okay, so does that mean that every light bulb lasts 1,000 hours? No. It just means that on average, the light bulbs last 1,000 hours. Some of them are going to be less than 1,000 hours. Some of them are going to be more than 1,000 hours. And then let's say that we also take some data and calculate a standard deviation. So how far these measurements of location fall from our mean. In other words, how much do they vary? So maybe the standard deviation is 100 hours. So again, looking at what we have right now with our distribution, if the mean right here is 1,000, then one standard deviation from that, below that mean, so 1,000 minus 100, would be 900. One standard deviation above that, so 1,000 plus 100, would be 1,100. And we can expect most of the light bulbs to occur between these 2 points. Most of them are going to have a lifespan somewhere between 900 hours and 1,000 hours. Still making sense? Okay. Now let's go one step farther. Maybe we don't want to know general information. We want to know something really specific. Like, what is the probability that if we take one light bulb off the assembly line and test it, that it will have a lifespan of somewhere up to, not equals, less than or equal to, so up to 1,200 hours. So what we want to find is the probability that it will be somewhere either below or exactly equal to 1,200 hours. Well, for this we need to add another tool, another formula, which is called a z-score. Z-score is calculated by taking the x value, whatever point we're looking at, in this case 1,200, and subtracting the mean. So find the distance between this point and the mean. How far is it away from this middle point? And then divide by the standard deviation. That's it. Thankfully, this is a nice small formula as opposed to some of the ones we've seen in the past. Okay. So what this will give us is a number that relates the position of this number to the area behind it. What I mean by that is if we again look at this standard deviation, I'm sorry, not standard deviation, normal distribution. And again, if this is 1,000 here at the mean, but we want to look at 1,200, the z-score relates this position to the area behind it. So all of the data behind it. Does that make sense? Okay. So let's go ahead and plug in some numbers here. Again, z equals x minus the mean. So x in this case is 1,200. Minus the mean is 1,000. Divided by the standard deviation, 100. So what's 1,200 minus 1,000? Yeah, 200. Okay, now what's 200 divided by 100? 2. Okay, so this number doesn't tell us anything quite yet. Again, it's just a relationship between the position of this to the area behind it. We need to use another formula to get the actual probability. Now, I say use another formula, I'm actually lying. There is a formula that you can use to get the probability from this, but no one in the real world uses that formula. Instead, because that formula is so well understood, we have charts. So this is what's called a z-table. And what it does is it has z-scores listed across the side here and the top. So the first two digits of your z-score are on this side, and the third digit is on the top here. And so what you do is you find the number for your z-score, whatever it might be. So maybe first one is 0.9, and then the second one is 6, so a total of 0.96. Well, you'd have a z-score equal to this probability. Does that make sense? Okay, but what we have here is 2. So I need to look for 2 on my z-table. Now, as a decimal, what is this? It's 2 point what? 0. Yeah, we don't have anything behind it. It's 2.0, technically 2.00, since we need 2 decimal places here. Okay, so first thing we need to find is 2, so we look down here. There's 2. And then we need to look for those decimals, so 0.0, well that's 0.0 right there. And so where do they intersect? Right there. This gives us our probability. This is the area behind, again, the area behind that point that we're looking at, right there. So what is this number? 0.97725. So this is the probability that if we selected a light bulb at random off the assembly line, that it would have a lifespan of 1,200 hours or less. And of course, make it a little bit more easy to understand, we can make this into a percentage instead by moving this decimal twice to the right. And so we have a 97.725% chance of selecting one within that area. So within this area here. Does this make sense? So once again, by calculating this, we see that, again, selecting one at random, there's a 97, almost 98% chance that it will have a lifespan of 1,200 hours or less. Any questions? No? Okay. Oh, and I was asked this earlier. Yes, I will provide these charts to you for a quiz or exam. It'd be barbaric of me not to. All right, so that's the basic idea behind the z-score. Again, what it does is it calculates, or helps you calculate area, or probability, behind a certain point. So let's try another one. Let's think about height of people, maybe height of people at the university. Okay, so everybody at the university has to take at least one physical education class, and typically one of the things that you do in the physical education class is you get your height and weight taken. Let's just look at heights right now. We can expect that height would be a normally distributed set of data. So again, what I mean by normally distributed is that the frequency would be a gentle curve like that. And again, the middle would represent the mean, median, and mode. So looking at our data for people's height at the university, we find that the mean is, let's say 5 and 7/10, or 5.7 feet. Which is what you'd expect in the real world. Everybody is going to be somewhere around just above 5 feet. And then you have people like me, you know, that are 6'7". falling outside of that range. Then you also have people who are, 4 feet, something like that. You also have people who are have the genetic condition gigantism and dwarfism. Now, are there a lot of people with those conditions? No. That's why there's very little frequency there. But again, most people are going to fall right here. That's why it's such a high frequency. All right. So again, mean, or mu, is 5.7 feet. And then we also find that the standard deviation for our data is 0.3 feet. Okay? So, what we want to know now is what is the percent of people that are 6 feet or below. So 6 feet's probably somewhere around here. This is our x value. So we want to know the percent of people who are 6 feet or below, that area right there. Well, it's the exact same thing we just did. We need to find a z-score. So once again, our z-score is z equals x minus mu all over standard deviation sigma. So let's plug it in, see what we get. So z equals, let's see, 6 minus 5.7 over 0.3. Get my calculator out here. 6 minus 5.7, whoops, 5.7 is 0.3. And what is 0.3 divided by 0.3? 1. Okay. So again, we need to look at our z-table and look up this score. So here's the z-table. Again, we have a z of 1. So we look down through here. There's 1. And what is the decimal that comes after 1? Well, do we really have a decimal after that? No. So what would be the next part? Is it 0, 0.1, 0.01, 0.02? What are we looking at? Yeah, just 0. There's nothing that comes after that 1. So 1, 0.0, and it intersects right here at 0.84134. Okay. So our probability is 0.84134, and as a percent, that is 84 about percent.
Are you all usually after the decimal or the percent?
I will tell you which one I want per question. Okay. Typically, I'll accept either one. Like this past quiz, when I was asking for probabilities, some people gave me a decimal, some people gave me a percent. As long as it was the correct one of those, I gave the points. But again, if we are thinking about, okay, how many people fall at 6 feet or below, 84% of the people in this data are 6 feet or under. Okay? Any questions? All right, good. Now, what we've been looking at so far is data that, or I'm sorry, an x value that falls above our mean. Now, of course, we could do this for anywhere along this data. So what about a data point that falls below our mean? Well, let's take a look at that too. So once again, we have a standard normal distribution. And sorry, I don't have an example for this one. I just made up numbers. But the mean is still right here in the middle, and we're going to say that for this example, our mean is 79. Okay, and let's say standard deviation is 13. So, what if we want to know how much of our data falls below or equal to 54? So again, this is a x value, a data point that is below our mean. So all the ones that we've been looking at so far have been somewhere over here. This one is, somewhere around here. Well, that means that we're looking at still the data behind that point. Well, if we look at what we've been doing, just pull that back up. If we look at what we've been doing, this is a lot more area than that is, isn't it? So we can expect that this is probably going to be a smaller probability or a smaller percent. Now, is it calculated any differently just because we're below the mean? Actually, no. It's the same formula. Z equals x minus mean over standard deviation. So we'll go ahead and plug these numbers in. So 54 minus 79 over 13. Okay, 54 minus 79, is that going to come out to be positive or negative? Negative, and that's important. Anytime that your x value is less than your mu, your mean, that'll come out to be negative, making the entire z-score negative eventually. Okay, so negative 25 divided by 13 is negative 1.923. Okay, so it's important that z-score is negative, because what we've been looking at so far, well, I only see positive values on here. So we actually have a different table that we need to use for negative values, which I have right here. Okay? So same idea. It's still a z-table. It's just this is a negative z-table, but it does the exact same thing. It calculates the area below a particular point. So we need to find negative 1.9. So scroll through here. There's negative 1.9 right there. And then the next digit is 2. So there's 2. Scroll down, and they intersect here. And that is 0.02743. So both these tables do the exact same thing. It's just that one of them is for positive z values, one of them is for negative z values. Okay. And of course we can make this into a percent. Just move that decimal twice to the right, and we get 2.743%. Okay, make sense? Good. Now here's another question for us. Everything that we've been calculating so far has been x is less than or equal to this number. So what we're doing is we're calculating the area behind a particular value. But what if I flip that? So now x is greater than or equal to 54. Well, what that would mean is that now I'm not calculating the area behind that point. I'm now calculating the area in front of that point. So this whole thing right here, I'll indicate that with polka dots. Okay. Well, both of our z tables, they calculate behind. Well, what do? We can't get it then. We know how to get our z-score. We know how to figure that out, but we can't get that because we don't have a z-table for it. Well, there's a reason there's not a z-table for it. It's because it's extremely easy to get your new value. If you want to calculate above, do all this. Get this number here. Okay? Again, this is the probability of things landing in, this is the probability of things landing in this area back here. We need to think about what we said at the beginning of class today. Again, a normally distributed set of data, that mean breaks it directly in half, right? So 50% and 50%. Oh, it's 50% plus 50%. 100%. Yeah, obviously. Okay. So what this means is if we were to take a point at random from this set of data, there's a 50% chance it's on this side, there's a 50% chance on this side. But there's a 100% chance that it lands somewhere on here because it's got to be somewhere in our data, right? Well, we've been converting probabilities to percents. Let's go the other way around. Let's take this 100% and turn it into a probability. What would 100% be as a probability instead? 1. Okay, so the entire thing represents a probability of 1. But we've calculated this side as a probability of 0.02473. So what if we just subtract this side? Take it off. What would we be left with? Well, we'd be left with this side, the stuff that's higher than 54. And that's literally what we're going to do, is subtract this side from 1. So 1 minus the probability below will give us the probability above. Okay, so let's go ahead and do that. 1 minus 0.02743 gives us 0.97257. Make sense? Okay. Okay. So that's why we only have these z-tables. Now, if you look online, you can find z-tables that calculate above, but they're mostly useless because you can just take this and subtract it from 1 and get the same thing. But that's why we only have these z-tables that calculate below. Okay? Now, we can calculate above, we can calculate below. What if we want to calculate not above or below, but between? Okay? Well, I will leave y'all to think about that one, and we will cover that on Friday. Okay? Now, what I've taught you today already gives you all the information for you to figure this out on your own, so I want to see if y'all can figure it out. Alright? But, again, we'll talk about that on Friday, and we'll go a little bit early today. So I hope y'all have a great day, and I'll see you then.